key papers and books over the last decade. He's here this week working with members of the Kudos Centre of Excellence in the context of a new program that actually looks at the intersection of quantum mechanics and nonlinear optics in particular, which is the topic of his talk today, looking at nonlinear quantum optics. So it's my pleasure to introduce Professor John İ.Sipe for the first IPOS seminar.
Thanks, Ben. It's a great pleasure to be back in Sydney and have the opportunity to tell you about some of the work we're doing, and hopefully some of the sort of stuff that follows from this is going to be in collaboration with some people here. So the students who have really done the work and the postdocs, now they don't really look like that. Since I'm talking about rings, I went to a sort of Lord of the Rings motif here. But Luke Helt is the main student who was involved, and the other ones are former students and postdocs that have been involved in some of this work. So you all know that probably the easiest way to confine light at least a little bit is to put a high dielectric layer on top of a cladding, and then you make a waveguide. You make an integrated waveguide, and light will propagate in that waveguide, but of course it'll still diffract as it propagates along. If you shorten that, narrow it down and make it into a channel, then you can get light to propagate along the channel without diffraction. And of course, this is widely used in a number of applications. Here's one where it's used in multiplexing, where the different phases that the light picks up in the different routes, the different channels, is used to sort out different wavelengths. It's used in applications in biosensing. It's used in combination with microfluidics to move particles around near surfaces. It's used for optical processing. This is a Kudos application, and indeed a large part of the Kudos strategy is based on the idea of being able to move light around controllably in channels in an integrated structure. One of the problems is always scattering loss from these kinds of structures. So quite often one puts a cladding around the core to sort of minimize the effective surface roughness so the light doesn't sort of wander away from the channel that you're trying to get the light to go in. But there's some wandering that's actually useful, and that's the kind of wandering you can get when you add ring resonators to the kind of channel structures. These are some old examples from Bob Boyd's group at the University of Rochester, and you can see what they are here. They're just ring structures connected up with channels. There's the kind of two-channel variety. That's the top one, where there's two channels, and then in the bottom case you get an example of a one-channel structure. Well, I can't point here, but you can see that there's just where the ring is on top there. There's just one channel by it. That's okay. Yeah. He's small beans. Yeah, right. Not of the sticks. Okay, so those were made out of gallium arsenide. A lot of these structures have been made out of gallium arsenide, and there's a high index layer there. This is not going to. You can see it there, that green thing. Okay, and that's where the light is. That's where the light is confined. It moves. Pardon? Oh, that would be great. Thank you. Okay, great.
The bottom one should be red.
Bottom.
It just was.
I just killed it. I'll do without it. That's okay.
Sorry.
Oh.
I see it splits in the light as well. Just the bottom.
Okay. Thank you. Cool. Okay. Good. So you can see how the light is confined in these structures. If you actually have it going around in a circle, the centrifugal force pulls the light out a little bit to the side, but it propagates with a kind of effective index that's the wavelength in vacuum divided by the effective index in the channel. So I mentioned there's a kind of there are two-channel structures and there are one-channel structures. Let's look at the one-channel structure first. If light comes in, since there's some distance between the ring and the channel here, if things aren't right, mostly the light's just going to go straight through. It's not going to go into the ring at all. But if you get a special condition, if you get a resonance condition where there's an integral number of wavelengths, inside the ring, then the light can be tempted to couple in evanescently, and it can spend some time in the ring itself, before it eventually marches on and goes out. I sometimes refer to these things as photon hotels, because the photons can check into the hotel, they can stay in the hotel for a while, and they can check out again. The two-channel structure works in much the same way, but it sends light in the backward direction after it spends some time in the photon hotel. So the two-channel structures can act as filters. At one of those special wavelengths, they will send the light going back, and you'll see a dip in the transmission spectrum. The one-channel structures ideally send everything forward, but of course, since at certain frequencies the light spends a lot of time going around in the ring, there's an enhancement in the delay time, and you therefore get a modification of the phase of the light as it goes forward past the photon hotel. So these structures give you a way to control the phase and the amplitude of light. That makes them very powerful devices. They've been used for optical filters, add drops. They've been used in investigations of slow light. And indeed, there's a company, it's gone through a number of iterations, but it's now part of Infinera, that makes these and sells them as commercial devices. Here's what some of them look like. You can see the ring structure at the very top there. There's the ring, there's the bus that connects it, and the diagram on the right there shows you how the light is distributed when it's going around in the structure. And here you can see this is a double channel structure, so you can see the dips associated with TE and TM modes. The Qs here can be very high. The Qs of these structures are about, of these, happen to be about 65,000. Okay, now my interest, or the interest I'm going to focus on today, is not so much the use of these things in linear structures, but the fact that the enhancement in delay time, of course, leads to an enhancement of intensity in the ring, because the intensity can build up inside, and that's going to lead to an enhancement of nonlinear optical effects. That's what I want to focus on today. And this is to some extent an old story. The first such enhancement that I was seeing, that I'm aware of, was seen back in 2000 in gallium arsenide structures, where they in fact looked at four-wave mixing and saw an enhancement of four-wave mixing in one of these ring resonator structures. So this whole topic is close to 10 years old now, but I think there are some interesting aspects of it that are worth looking at again with respect to quantum nonlinear optics, and that's where I'm eventually going to get. Now, when one talks about nonlinear optical processes, they basically, at least at one level, come in two varieties. There's the so-called Chi-2 processes, which unfortunately are sometimes called three-wave mixing process, which is a confusing notation. Then the Chi-3 process, which is sometimes called four-wave mixing processes. So you have to try to keep this notation straight. The two-wave, the Chi-2 processes are things like second harmonic generation, where you get two photons of frequency omega to fuse into one photon of frequency 2 omega. And to get these kinds of processes, you need a material such as gallium arsenide where there's no center of inversion symmetry. Okay? Chi-3 processes are more general. They exist in just about anything, including glass, silicon dioxide, for example. So they exist even if there is a center of inversion symmetry in the material, or even if the material is amorphous. And they involve, well, something like, one example is the one I gave here. You take two pump frequencies and a signal frequency at a little bit higher frequency, so blue, higher frequency than green, and you get a little kind of a optical reaction here in which you end up with two photons at the higher frequency and an idler photon at lower frequency. Okay? So energy is conserved here because the omega I is lower than omega p by the same amount that omega s is higher than omega p. But you see, you've changed the color of the color of the photons that's coming through. So this is a four-wave mixing process. It allows, for example, for you to make new frequencies. Okay? Now, most of the work I've actually done on these kinds of processes